Идет, да? Звук. Ну, звук должен быть, настройки все как обычно. Okay, there is one little section that we need to finish in the chapter about graded and filtered modules. So if I remember correctly, this is section 8.3. So this is Hilbert's series and polynomial. So this will be especially important in the next chapter about dimension theory. So first of all, let me fix a graded ring. So A is graded Noetherian ring. Almost everything that we're going to do until the end of this course will be about Noetherian rings. Noetherian ring. And also let's fix M to be a finite, of course graded again, graded finite A module. And also we need to choose function lambda. So let me say choose lambda, an additive function with z values. Okay, so additive functions with the values on. So I'm going to say what it means to be additive. So on finitely generated A0 modules. So additive here means the following thing. If you have a short exact sequence, so M prime and the M double prime, so then the lambda of the M is the same thing as the lambda of the M prime plus the lambda of the M double prime. So this is what it means for a function to be additive. So you can associate an integer with any module and you have this. Of course, if you have this for short exact sequences, you have this for exact sequence of any length, you get the just alternating sum of all the lambdas is equal to 0. So for example, what function we can say, so for example, well, first I can assume that lambda 0 is Artinian, and then in this case lambda is just the length function. So if this is Artinian, if this is finitely generated, then this means that this is also Artinian, Noetherian, so it's finite length, so it will be finite number. And the special case of this one, the 2, is this is just the case where A0, say K, is a field, and in this case lambda is just the dimension over K. So in many examples this is enough, and to be honest I don't even know other examples other than these two, what lambda we can use. So when I think about Hilbert series and Hilbert function, usually I think that A0 is a K, so and the function is just the dimension. So it's enough for many examples. Okay. Now we need to introduce the following notion. So let me do it here. So definition. So terminology might be different. So I am going to say the Hilbert series of M, and sometimes people say the Poincaré series. Well, this terminology with the Poincaré is more standard for topology, but this is essentially the same thing. This is generating function of the dimensions of the components of M, and dimension with respect to this fixed function lambda. So there are many notations. There is a kind of long notation, HS, which states for the Hilbert series. You can find this in some books. So this depends, of course, on the module M, and as the generating function, it depends on some formal parameter T. But I'm going to prefer shorter notation, just P. This is for Poincaré. So again, P depending on M and T. And by definition, this is of course just an infinite series of the lambda Mn T to the N. Yeah, so yeah, so this is just a component of degree n. So this component, if we assume that this is Noetherian, we proved that in general this means that each component is a finite module over A0. So this makes sense. This is supposed to be a finite function, finite number, finite integer lambda.
So we don't grade it that below 0.
No, we only consider n greater or equal than 0. And about this series, we can prove the following fundamental theorem, which sometimes is called Gilbert Ser Theorem. So suppose A is generated, by elements x1 up to xs. So in this section and the next chapter, S would be my standard notation for the number of generators. So these are generators, and also my standard notation for the degrees of the generators will be ki. So ki, by definition, degree of the xi. So where I is between 1 and s. So then I have the following claim about the Hilbert series or Poincaré series. So P of mt has a very specific structure. It's not just any random series. It looks always as a polynomial f of t divided by product over. So in the product I take all the i's for the generators between 1 and s, and have 1 minus t to the ki. So yeah, so for any finite A module M, and I also need to say that so with f of t being just a polynomial with integer coefficients. So in particular, the claim is that this function, this Poincaré series, is always a rational function. So proof by induction on the number of generators S. So let's start with the base of the induction. So the base, in case S is equal to 0. So what we can say in this situation? So, well, there are no generators, meaning that A is the same thing as A0. So if in this case we can say that, well, since And we assume that this is a finite module, so I claim that Mn is actually 0 for n sufficiently high. Right? Is it clear why there are no components? Well, after.
Not really.
Well, M is finite. This is important. So it has some set of generators, right? So each generator, well, this is a also graded module, so each generator can be chosen to be homogeneous. So generator sits in some, say, degree 1, 2, 100, 200. So when you multiply, potentially if you have some higher degrees here, you can move them to any degree you want. But when you have only a 0, all the products just stay in these degrees. So there are no anything higher than the degree of the highest degree of the generator of M. Okay, but then I claim that we're done with the induction. Well, if there are no components, this thing is just a polynomial.
Yeah, and lambda of Mn should be the integer.
It's always integer. It is fixed to be an integer. So, but in this series, there are only finitely many terms. Hence, the answer is just some polynomial as we claim here. So there are no denominator in the formula. Okay, so this finishes the base of the induction. Now, let's try to do the step of the induction. So, step. Well, I choose a homogeneous element. So let's, well, no, not really. I'm considering just the last generator. So let's take the last generator XS. So then, if I multiply something in the component Mn by this generator, so I'm getting something in the Mn plus Ks, right? But potentially I have some kernel and co-kernel. So let's introduce some notation. So let's say that something in the kernel will be Kn. So this is the component of degree n of the map, which is multiplication of the XS. And there is some co-kernel. Now let's call this L. And since this is a quotient of the n plus Ks, so let's call this L with n plus Ks. So we get such short exact sequence. Well, the module K and the module N are finite A modules. So, as a kernel of an Aetherian module, this is a submodule of an Aetherian module and the quotient of a finite module. This is again finite. So these are finite A modules, and both annihilated by the generator XS, right? So clearly K is by definition being a kernel, and on the co-kernel we just set XS to be to act as 0.
So consider every short exact sequence for every n, and
No,
construct K.
no. S is fixed, so S is the number of generator.
Mn is not fixed. I understand.
Oh yeah, you consider all the degrees, yes. So this is for all the degrees. So this is true for any n.
When's L annihilates by XS?
Oh, that's a co-kernel. So this is essentially like saying that L is the quotient of the M modulo XS Mn, XS M, so L.
Oh, yeah.
So L is M XS M. So by definition, XS annihilates M. Okay. So now let's take this short exact sequence and apply lambda to the short exact sequence. So then we get the following identity. So lambda of the Kn minus lambda of the Mn plus lambda of the Mn plus Ks minus lambda of the L plus plus ks, and this is all equal to 0. Oh, since lambda is additive. Okay, so the next step is to multiply by t to the n plus ks, and well, I'm not going to write this as a word, so let's take summation over O(n) greater or equal than 0. So to get generating functions. So you take this identity, multiply everything on this thing, and take the summation. So then I claim you get the following identity. So 1 minus t to the ks times the Hilbert series of the module m, and this is equal to the Hilbert series of the Lt minus t ks p kt plus potentially some polynomial with integer coefficients. So let's try to understand how I get this formula. Well, when you multiply this identity by this power, well, by the t to the n ks, well, what you get? Well, first of all, look at this term.
It will be just PMT.
Yeah, so this corresponds to this part. But not quite, because well, you get this thing, you need to change the index of the summation, right? Summation is over n, but you need to take summation over n plus ks. So by this shift, you won't count first several terms, and this is why I have this additional term.
Okay.
So then you do when you consider the product like this, take summation over n, you get exactly this. And then you do for this and this by exactly the same reason, but I just move this to the right hand side, right? This thing and this thing. And so what's left is
just PLT,
yeah,
without some.
without some polynomial, which is again hidden in this additional g of t. Okay, end of the proof. All right, because now what's left is we just divide by 1 minus this t to the ks, and since this is already true for L and K by the induction hypothesis, so the result is true for the M.
Like, why for PLT and PKT it's just polynomials? Because they...
No, these are not polynomials. These are elements of this particular form for all the generators except the last one. We show that the generator xs acts as 0 on the L and on the K. So we apply the theorem for all the generators except the last one. So PL and PK has this structure, but I need to write s minus 1. And then what's left is just polynomial over right denominator, polynomial over right denominator, and just divide by the denominator that is missing. So I'm not going to write these formulas, but I think it's quite clear. Okay. So maybe I introduce immediately some little definition, which going to be important later when we study dimension. So there is an invariant of the module, which is actually one of the ways to define the dimension of the module. Well, you just take the order at the point t minus 1 of the Hilbert series. So that's a rational function. Clearly at the point 1 with respect to the variable t, it has some pole. So the order of this pole is the dimension. This is one of the definitions of the dimension in terms of the Hilbert function.
This dimension defined only for if A is generated, is clearly generated.
No, everything concerning dimension defined for Noetherian rings and finite modules. So the dimension theory is something that works for Noetherian rings, at least how I know the dimension theory. So maybe there are some generalizations, but we're not going to discuss that. So and essentially the dimension theorem, the main theorem of the dimension theory, is just that this number d is the if you instead of m just plug in the ring. Well, you need to modify this slightly. We're going to do this probably today to work with local rings, not just graded rings. So this number is equal to the group dimension and is equal to one more number. So these three numbers are equal. So that's the dimension theorem. But before we do this, let's prove one more proposition. And the next proposition I'm going to leave as an exercise. So in this proposition, I'm going to assume some simplifying thing. So I'm going to say that ki I all equal to 1, right, for I between 1 and s. So all the degrees are in 1. So sometimes such rings are actually called homogeneous rings in some literature. So when everything is generated in degree 1. So then lambda of mn is a polynomial. In n. So we consider this as a function. So, and there is also a name for this. This is called Hilbert function. So there's Hilbert series, which is generating series. Hilbert function, which is just a function from integers, the n to the integers. And in this proposition, we're going to see that there is a Hilbert polynomial. So is a polynomial in n of degree d minus 1 for O(n) sufficiently large.
What's is a polynomial in n?
Oh, as a function on n, this is a polynomial function. And this is exactly what is called the Hilbert polynomial of the m. So if we have d is here.
So of degree d minus 1.
So if you want, yeah, you need to say that d of m minus 1. Okay. Well, first of all, let's say that d is d of m, as I tried already. So for shortness of the notation. So then the Hilbert series, which is of the form. Oh, actually, when I taught this course before, I saw that there is a confusion that sometimes people think that this f is the Hilbert polynomial. That's not true. It's just some polynomial that we get in this theorem. The Hilbert polynomial is a different polynomial.
What is Hilbert?
So this will be a polynomial in the for large n. This is a polynomial. So that's the Hilbert polynomial of the module.
Okay.
So the claim is that you can compute this function of n as a polynomial, and this polynomial is called Hilbert's polynomial. Okay, so not this one. This is different. This is just a numerator of the generating series. Okay, so the identity that we have is this one, which is more or less just repeating the definition with the different index of summation. Okay, instead of yeah, and also simplification, since when everything is in degree 1, generated in degree 1, so this denominator is now this one. Okay, so so what we can say that without loss of generality, I can assume that S that I wrote here is the same as D. And also f of 1 is not equal to 0. Otherwise, I just cancel some power. So
okay, if f of 1 not equal to 0, I understand why s equal to 0.
Well, because I can do the cancellation. So if I have some powers of the 1 minus t in this polynomial, I just cancel in such a way that 1 is not a root of f. So there is no 1 minus t in the numerator, and then this is uncancelable. So this s that I'm going to write here in this presentation. So I'm just want the same structure. I want polynomial over such product. If I just want a polynomial over such product without loss of generality, I can say that s is equal to d, because otherwise I can just cancel the power of 1 minus t in the fraction.
So for this polynomial, if f of t don't have a root of 1, the order of t minus 1 is like minus s. Am I not right?
No, the order is exactly S. This is the order of the pole.
So,
So if f of 1 is not equal to 0, the pole of this rational function has order as exactly S.
okay, let's take f of t be 1. Just 1.
Okay.
1 over 1 minus t f power to the n. The order of this polynomial is S. Like 1 divided by 1 minus t power to the s.
I see. So
I think the order
you want to say that there is a minus here, right?
I think
Yeah. What I meant this is the order of the pole. So if you just consider this as an order of pole or 0, so I guess you need to say that this is minus.
okay.
Yeah. So that's the order of the pole. Okay. And now we need to do some little explicit computation. So we can say that the f of t is some polynomial. So let's write this polynomial. So this is k running between 0 and some large n. So a k t k. Now, well, I hope you still remember how to compute coefficients of this explicit function. So notice that this is actually the Hilbert series for just the symmetric algebra.
Why?
Well, that's clear. For example, if you can prove this by the induction of the number of variables. This is I'm going to leave this. Well, we're going to do this exercise on the seminar. So, but anyway, you can notice that this is a Hilbert series for the symmetric algebra, or you can explicitly compute this thing. So you can say that this is the sum over k, so the summation over k, and then the coefficient here is d plus k minus 1. Choose d minus 1 t to the k. If you just do this explicit combinatorial computation, then you can notice that the coefficient here is exactly the coefficient, this binomial coefficient is exactly the number of the homogeneous polynomials of degree k in d variables.
Yeah, you will use notation S or notation D?
S is d.
Yeah, no, but okay, it doesn't matter.
Yeah. So okay, so you're right. Maybe I need to change that this is d. Okay. So then we have a formula for the lambda of the mk, since this is a product of two series. Just one series happened to be a polynomial, and the other series we have explicit formula. So lambda of the mk is the sum. Okay, I now want to choose to the lambda n, since I want to use k as the summation variable. So computing this as a product of two series, I'll get this thing.
First it's D, yes. D plus n minus k minus 1.
Yeah.
Okay.
Yes, and yeah, I think that's all I need. So that's just an explicit formula for the lambda of the Mn. Now, so there is some sum, but if you look at the H binomial coefficient, well, for sufficiently large A, you can think about this as a polynomial function. So that's essentially, this is the end of the proof. So maybe one more thing, if you want to compute the leading term, so the leading term in terms of the variable n will be the following. You take the sum of all the coefficients a, k in this polynomial, then there will be n of the degree d minus 1, and then you need to divide by the d minus 1 factorial, plus some lower order terms. Or you can rewrite this as f at 1 n to the d minus 1 divided by the d minus 1 factorial. Just in case.
Mn as a sum like this.
Mm-hmm.
And it's a sum plus something.
Here, I'm just computing, essentially what I'm doing is just computing the coefficient that I'm supposed to put between the highest, the leading term of this polynomial with respect to n.
Yeah, and coefficient will be sum of some coefficient, yeah?
The coefficient will be sum of all coefficients, so this is summation over OK. Okay, so definition, the polynomial in the previous proposition is called the Hilbert polynomial of M. And there is notation, say H, P, so again for the Hilbert polynomial of the M, and this is a function of n, and this is the same thing as the lambda of the Mn, and this is for n sufficiently high. To say that the binomial coefficient is the polynomial function in n. I'm skipping some elementary computations, so you need to understand exactly why this is polynomial function, but you just write the formula for the binomial coefficient. And also, not very hard to find the leading term of this polynomial. Again, you can see from this kind of explicit computation that the degree is d minus 1 as promised in the statement. So I want to formulate one proposition and postpone the proof of this proposition on the seminar. So if we take x of some specific degree k and which is regular, if x is regular on M, remember that regular means just not a zero divisor on M, so multiplication on this element has no kernel on the module M. So then we have the following. Yeah. Yeah. Well, no. We give the definition of regular element when they discussed associated primes. That was the definition of regular element. So then we have the following. If you want to compute the d of the M modulo xm, then this is d of M minus 1. So not a very hard exercise. Just don't want to waste some time on this. So, and with this, I'm going to start new chapter, the last chapter of the course. Well, the global dimension is just the supremum of all the dimensions of the all projective resolutions or modules. Well, it's kind of a little bit different.
Well, kind of this form, they have theorems, like change of ring theorems. I think third or second looks like this.
Yeah, well, the correct statement is that if the ring is regular, then the global dimension of commutative ring, global dimension is the same as dimension we're going to discuss. But interesting examples, for example, when you have a singularity, The group dimension still could be finite, but the global dimension is always infinite. For finite global dimension, it's exactly one of the possible definitions of the regular ring. It's an equivalent condition. That's Ser's theorem. So what we're going to do is a little bit different. So I think it's chapter 9, Dimension Theory. So first 9.1, the Hilbert. Well, sometimes people say Hilbert, sometimes people say just Samuel. So Hilbert Samuel function and polynomial. So we need to. So the dimension theory is for local Noetherian rings. So the main result for local Noetherian rings. So we need to modify what we know for graded rings to work in the situation of the local rings. So, and I start with the proposition, which is essentially already known for us. Oh, before I start, I'm going to use this. Well, actually I need to write this before the first section. So what I need to write that all rings are Noetherian and all modules are finite. So this is my assumption for this whole chapter. Okay, so if we have a local Noetherian ring, and we have ideal Q in the R, then the following are equivalent. So 4 conditions. Condition 1, quotient by this ideal Q is Artinian. Condition 2, there is such positive n integer such that m to the n is contained in Q. 3, Q is m primary. And 4, the radical of Q is m. Well, in fact, we know already that 2 is equivalent to 3 and equivalent to 4. We discussed this when we discussed the primary ideals, and in the case where they are m primary, where m is maximal ideal. So 1 is equivalent to 3 and equivalent to 4. So C chapter on primary decomposition. This is just something not really new. Well, we need to show that, for example, 1 is equivalent to 2. So 1 implies 2. Okay, so what we know? We know that this is Artinian, and since we take a quotient of a local ring, this is still local. So this is local Artinian. Well, what's the new radical of this local Artinian ring? Well, since this intersection of all maximal ideals, well, this is just, there is just one ideal M. So then M to the n is, or is 0 in the R modulo Q. Right? Every element in the M is nilpotent, so we have this. Well, maybe to be completely formal, I need to write something like this: M modulo Q. This is ideal M in the quotient ring. So, and here, and the same I need to do here. That's the same thing, but written more formally. So, but if we have this, well then clearly we have condition 2. So let's go in the other direction. 2 implies 1. So we need to show that this is Artinian. So let's take a prime. So let's call this P, such that Q is contained in P. So in other words, I'm just taking a prime ideal in the R modulo Q. Well, I know that M to the n is contained in the Q, so hence I can say that Mn, well, M to the n is contained in P. Then just take the radical of the left-hand side, the right-hand side. The radical of the left-hand side is M, the radical of the right-hand side is P. So M is contained in P, M is maximal, M is equal to P. So radical. M is equal to radical. No, see, we have this and we have this.
Why is radical of P is P?
Oh, if you take any prime ideal, if any prime ideal, raise it to any power, take the radical, it's still P. So M is contained in P, M is maximal, hence M is P. So, is it clear that the ring is Artinian now?
Well, now our maximal is prime, so
Yeah, so, yeah, and there is only one maximal. Or we can say, for example, the dimension is clearly 0. Yeah. And the Artinian ring, as we proved in the chapter about Artinian rings, is an Artinian ring of dimension 0. So this finishes this proposition. And this proposition allows us to give a definition. In fact, we're going to see four equivalent definitions. So ideal, as in previous proposition, is called a parameter ideal of pair R and M, no, of the local ring Rm. So let's say this is first part of the definition and the second part of the definition. So if I choose generators, again I'm going to call the number of generators S. So then xi's are, no, x1 delta xs is a system of parameters of this local ring.
So like parameter ideal is just M primary ideal?
You can use any definition that you want. All these conditions are equivalent.
Yeah,
So essentially it means that if you choose different textbooks, you can see different definitions of the parameter ideal. So well, I like the first definition. Essentially, it's saying that, well, for example, if you take something like this, then it's quite clear what are parameters. The system of parameters are exactly these variables, since the quotient. Well, in this case, you just take Q to be the maximal ideal. So this will be the system of parameters. But in general, the system of parameters is kind of covers all the ring except the kind of fine dimensional part, which is the quotient. Okay. Yeah, and just to give you a geometrical intuition, if you remember the geometry of manifolds from the third semester, many computations were done by you look at the point, you choose a local system of coordinates, and you do something in this system of coordinates. Well, this is how you do this in algebraic geometry. If essentially you take algebraic variety, you choose a point. Well, if this is a closed point, then you get already a local ring. If it's not a closed point, you can localize it, corresponding prime ideal. But let's pretend this is a closed point. Then you get a local ring, and in this local ring, you can choose the system of parameters. And this would be something like local coordinates for your variety in the neighborhood of this point.
And they will be glued.
In algebraic geometry, it's not a very good idea. So you need shift theory to say this properly.
I think skids are glued on affine skids.
Yeah, that's the definition, yes. Okay. Next proposition. So if I'm going to write this as before, Mn is a stable Q filtration. So I'm going to assume that Q is some parameter ideal. So where Q is parameter ideal. So then the length.
So like M is with two graded ring that's also local.
No, there is nothing graded here. We have a local Noetherian ring. In this local Noetherian ring, yeah, we have some module, and in this module we suppose that we have a stable Q filtration. Well, you can choose any stable Q filtration, but at least you have one, which is just the Q to the n, Mn. This is Q-adic filtration, so we always have at least one. So if we take any such filtration, then the claim is that if you consider a quotient M modulo Mn and compute the length, you'll get a finite number. Yeah, for any n. So this is for n greater or equal than 0. So in the dimension theory, we need filtrations, and we also need some aspects of the Hilbert function. So Hilbert Polynomial. Okay, so the proof is more or less straightforward. Well, maybe I just even skip a step and say immediately that if you consider such quotient, is it clear the claim that this is Noetherian? Right? Since ring is Noetherian, modulus finite, modulus Noetherian, Mn is Noetherian, Mn plus 1 is Noetherian, so everything is Noetherian. Well, since we have a stable filtration, so this module, Mn modulo Mn plus 1, is annihilated by Q. Just look at the definition when you multiply. Yeah. It's annihilated by Q. So hence, from this we see that this module is finitely generated over Artinian ring R modulo Q. And since it's finitely generated over Artinian ring, it has a finite length. So the length of the Mn modulo Mn plus 1 is finite. Now, if I want to understand the length of the M modulo Mn, now I kind of do this in steps. Well, if I just write the answer, so this will be the summation over, say, R running between 1 and n, a length of the M R minus 1 modulo Mr. Is this formula clear? It's from the filtration, right? You look at the filtration, you consider each of the embeddings, and you get the corresponding short exact sequence. So you get a bunch of short exact sequences where, say, Mn minus 1 is embedded into Mn, and you have a quotient. So essentially, separating a short exact sequences give you this formula. And that's all we need to show, right? We have a finite sum of numbers. Okay, so next proposition, which has more or less the same proof, actually. So for n sufficiently large, this length that we studied in the previous proposition is actually a polynomial of degree. So L of the M modulo Mn is a polynomial. It's a polynomial of degree less or equal than s. So remember that my s is now fixed. The s is just the number of parameters in some parameter ideal. So for now I'm fixing a parameter ideal q, so s is fixed, but there is also a question, what if I choose the different parameter ideal? Would it be different s? But we're going to address this question later. So now, for now, q is fixed. Okay.
Stable q flotation is also fixed.
Yeah, and the stable q flotation is also fixed, yes. There's also a question how this depends on the filtration. So again, let's postpone this question for several minutes. Okay, so we're going to reduce this to the graded situation. So we consider the associated graded using the parameter ideal q of the ring R. So let's say this is generated. So generated by xi bar, which is just the class of the xi plus q squared. Remember what's the graded thing is. It's just R modulo Q plus Q modulo Q squared. So it is generated by these things. It's just more or less by definition of this thing. Now what we can see that all the degrees of the generators of this graded ring are 1. Right? So they all sitting in degree 1. So this is in the Q modulo Q squared. So maybe I write it like this, belongs to the Q of R in degree 1, which is Q modulo Q squared. So this means that we can, for example, use arguments from the previous chapter about the Hilbert Polynomial, that everything is generated in degree 1, so it's a polynomial function. So if I consider the corresponding graded module over the graded ring, right? So the graded component will be this one. So I know that the length of this thing is a polynomial. So is a polynomial of degree at least s minus 1. Remember that in the proposition that proved there was d minus 1, so s minus 1. And of course, I need to say that it's for sufficiently large n only. Okay, now we'll just use this formula again. So, well, since there is a shift of the variable n minus, well, r minus 1, if you look at the leading term, you're going to see that you need not just s minus 1, but s.
If you shift it and sometimes n become not sufficiently high, what do you do with that? Like, we not choose that for like n.
No, you take n to be sufficiently high. If you
Yeah, but in this sum, there r could be equal to the 1 or 2. Like if it
yeah, but there are finitely many terms which will give you just some constant contribution, right? So up to some n0 there will be some constant, and then for higher than this n0 you get some several polynomials.
But can you explain why it should be polynomial degree, not at least s, at least smaller than s, and not smaller than n, s minus 1?
Well, yeah, I think that's a good question. So maybe we can, if I try to write the formula like this. So I have the length of the m modulo mn plus 1, so minus the length of the m modulo mn, right? So then, again, by looking at the short exact sequences, this will be the length of the mn modulo mn and minus 1, right? So let's see, can we derive this from this formula? So we know, no, plus 1. So we know that this is polynomial of degree s minus 1, right? So well, potentially I cannot say that this will be a polynomial of degree s, well, because I can.
You can say that this all polynomials of degree a lot, and they just disappear because of minus.
Yeah, that's true. Well, this is definitely something, just a computation with some polynomials, right? So I already know that everything is polynomial here. So we have polynomial here of the n plus 1, right? Minus polynomial at the n. And this is just some other polynomial, so maybe let's call this g, right? The degree of this thing is s minus, so the degree is bounded by the s minus 1, right? Yes. So the question is how we can see from this identity that the degree of the polynomial is bounded. No, I think we somehow I think it's some computation, or something if you just write this so explicitly in terms of the coefficients.
Maybe from this identity. Like there's n
Oh yeah.
Yep, it's yes, but for small terms, this is not a polynomial of degree s minus 1. So, like, if it's...
No. So we only need to kind of consider the worst possible scenario. Well, we have... So each term will be a polynomial of degree s minus 1, right? No more than s minus 1.
It's each term for sufficiently high n.
Well, that doesn't matter. Maybe sufficiently high term is just 1, and this is the worst possible scenario. If this is higher than 1, this is even better. Yeah, I think you're right. So if we have a sum of n polynomials, right?
Yeah.
And each of them has of degree no more than s minus 1 in n.
Yeah.
So then this sum is kind of no more than... Yeah, so I think we don't really need this. So just by looking at this formula, to summarize this, let maybe call this formula star. So by star, degree of what? L modulo mn is less or equal than s. Okay. So proposition. So we get ourselves, well, do I have a, okay, maybe I give the definition later. So we get ourselves again now a polynomial, that kind of numerical characterization of the Noetherian ring, but in this case the ring is just local, not graded. So we are adapted the theory from the graded situation to the local situation using this computation with associated graded objects. So the proposition is saying that the degree and leading coefficient of, I don't know, let me continue to write this as a function, so, but this is polynomial, so of this polynomial for n sufficiently high, doesn't depend on the filtration. Of course, filtration is still assumed to be stable filtration, but it could be any stable filtration. Okay. Okay, so the idea is the proof we have a canonical, kind of canonical stable filtration, which is just q-adic filtration. So let's compare any stable filtration to the q-adic stable filtration. So compare any stable filtration use q-adic filtration. Okay. Well, for any stable filtration, we have the following: that Qmn is contained in the Mn plus 1. Right. So then I claim that we have the following: Qn m is contained in the Mn. Now just use the fact that m0 is m, and then do this n times by induction. Okay, so if this submodule is well, if this is a submodule in the Mn, so at least I claim that they have the following inequality. So now the dimension theory going to look more or less like analysis. I'm going to write lots of inequalities. So the length of the m modulo Qnm is greater or equal than the length of the m modulo Mn. Okay, so this is what we have on one hand. On the other hand, we know that the QMN is the same thing as the M with the index n plus 1 for all sufficiently high n, right, just by the definition of the stabilization. So then I can see the following. M with the index n plus n0 is the same thing as the q to the n applied to the m n0. And this sits, of course, inside of the q to the n m. Again, more or less this is clear. Now, by looking at this embedding of these two modules, I can conclude that the length of the m modular mn plus n0 is greater or equal than the length of the m modular qnm. So I got these two inequalities. Now, comparing these two inequalities, I get the following thing, that the limit when n goes to infinity of the length m modular m with the index n plus n0 over the length of the m modular q to the nm. Well, what's this limit by these two inequalities? Yeah. So simple exercise in analysis. But if you know that this is a two polynomials, this is only possible when the degree is the same and the leading coefficient is the same. Well, we probably can derive more than that from this, but at least we get this. So this is why we have no dependence on the stable filtration. And now it's time to give a definition. So the Hilbert Samuel function of finite m module of finite, okay, so finite R module M with respect to some parameter ideal Q, so there is still dependence on the Q, well, is
So it depends on the choose of Q.
yeah, sure. So, well, notation is the chi M, Q, and N. Yeah, chi. So now this is just a function. So function on n. And as a function of n, of course, this is just the length of the m modular mn.
It's defined for sufficiently large n.
No. As a function, this works for any n, no, greater or equal than 0.
So it's function from like
from positive integers to again positive integers, since this is just some length. So this is a function. Now what we know for n sufficiently large, right? This is a polynomial. This is a polynomial. And its degree is denoted d of m. Well, it's in a different context. Before it was the diaphragm for a graded module. Now this is for any finite module over local Noetherian ring. Well, this is kind of independent definition, so I'm going to state it as independent definition. So one more invariant. So the delta of R is the least number of generators of parameter ideals.
Is D of n depends of n?
D of depends on what?
On n.
No. Oh, this will be a polynomial. So as a polynomial it has some degree. So there is no dependence on n if you just look at the degree of the polynomial.
Looking polynomial for some n.
No, as a function of n, this is a polynomial. So now we introduced one more invariant of the ring. So potentially it could be different parameter ideals with different number of generators. We'll choose the smallest possible. So proposition d of r is bounded by the delta of r. And we don't need to prove this. We already proved this. Right? We proved the proposition that the degree is bounded by the s. And that was for any, of course the argument works for any parameter ideal. So this would work for this delta of r, for the smallest.
So like D of r, isn't it depends on Q? D of n.
No, this doesn't depend on Q. Well, this doesn't depend. Well, I'm going to I'm going to leave this as an exercise. So the exercise, kind of with more precise exercise than just prove this. The more precise exercise is the following. And again, there's something that we do in the seminar, that the degree of the Samuel function. So I also need another notation. So let's say that the chi without m, right? This will be by definition chi for the ring. So if I don't write module, I assume that I'm working with the ring. So then for the ring, prove the following, that if you consider degree with respect to some parameter ideal, well, at least you can use as parameter ideal the maximal ideal itself. So this guy,
it's not depends. So for ring, it's not depends of
yeah. Well, I think it's also true for a module, but let's keep things simple, because we're going to prove the main theorem only for a ring. It also actually works for modules, but it requires more details and we just don't have time. So now we have this inequality. Okay, so do we have time to? Okay, maybe I'll try to prove the next proposition, but I only have 5 minutes. Maybe 5 is not enough, but maybe I can do this in 7 or 8. So essentially, what's the goal of what we're going to prove? The goal is to show that now we have d of r, we have delta of r, we have the crude dimension of r. So all these three numbers are the same. And we're going to, if you want to show this, we need kind of to show four inequalities. Right. Well, we have three numbers. Three. Oh, well, we already have one, but I'm trying to compute all the number of inequalities. So essentially, what we're going to do next time is just to prove more inequalities of this type. Then we combine them together, and we're also going to see that, well, all the numbers are the same. So that's the plan. But to do this plan, we need kind of this next technical proposition. So X is regular on M. M prime is the quotient of M modulo XM. So then the degree of the chi M prime with respect to Q is less or equal than the degree of the chi of the M with respect to Q minus 1. So that, I think in the graded case I left this as an exercise. It actually was quite easy exercise, but in this case, well, it's not, it's a little bit harder. So now let's say that N is XM to fix some notation. We have a filtration, so N with the index N it will be N intersect with the QM. So on the M we have this kind of q-adic filtration, and by the Artin-Ries. So Artin-Ries, this is stable Q filtration. Okay, so now we have short exact sequence. So N modulo N with the index N. This is mapped to the M modulo Q to the N M. And we have a map to the M prime modulo Q to the M prime. Well, little exercise that everything works with our definitions of the N prime. So then, computing the length of using every such short exact sequence for every n, we'll get length of the n modulo n minus chi of the m q of n. Well, just this is just notation for the length of the middle term, and plus the chi of the m prime with respect to the q as a function of n. So we get this.
So we need to prove that length of n quotient and n is 1. We need to prove that length of n quotient and n is 1, or more than 1.
Well,
Is it that what we need to prove?
yeah. So let's see how this works. So everything is supposed to follow by the fact that this is a stable Q filtration. We can say that Q.
smaller than that. Why the leading terms will be like disappear? That's not really.
Yeah, I think I'm missing an argument here. So
We need to make leading term disappear, yes, like this minus. So we kind of need to prove that he of MQN, the leading term of this, is equal to the leading term of length and quotient n.
yeah, and the claim is that this follows by the Artin-Ries lemma exactly. Since this is a Q-stable filtration,
Yes.
and this thing doesn't supposed to depend on the Q-stable filtration, it has to be always the same. But I don't see completely how this works at the moment. Okay, it looks like we're out of time, so maybe next time I still start with this proof and prove this with the details.